TWC, and as you've seen on the email, it's a very special TWC talk tonight. It's lightning talks for the grad students. Thank you to everybody that's signed up. The rules are approximately the normal rules for lightning talks at conferences and other venues. It's going to be 3 minutes, no props, only crib notes if you need them. There's going to be a bell that's going to ring at 3 minutes. You're done instantly at that time. The next speaker should be ready to go. Although I'll start the timer in a reasonable interval afterwards, after the previous speaker. You don't have to fill the 3 minutes. So if you finish what you want to say early, that's fine. And at the completion of every speaker's time, we're going to celebrate what they just said. Okay? So we're going to applaud. Applaud. We're going to applaud everyone. Everyone's going to feel like a rock star after this.
Right? And I'm going to ask one other thing, and it doesn't come out of your time, but please introduce yourself with your whole name, your year, and your major, because that way Christine can learn who you are, at least for those of you talking.
The timer will start after you've introduced yourself.
Who's on deck?
Okay, so Greg is about to speak. James is on deck. King is after that, and you are after that. All right? And let me find my. No, you introduce.
All right. I'm Craig Williams. Sixth year. Unclear at this point. PhD student. And ready to go? All right. My work is on Sparkle Federation, and this will hopefully be a very compressed preview of my proposal, which is hopefully coming up very soon. So the problem is you've got a Sparkle query, and you want answers to this query, but you don't know where all the relevant data is to it, right? You've all seen the big linked data cloud diagram, right? It may be on a whole bunch of Sparkle servers, or maybe some of the information is available as linked data, RDF files just sitting on a server somewhere. You don't know where all the data is. All you know is you want your answers, right? So my system that I've developed is all about taking your query and optionally an initial list of data sources that you may know about ahead of time, and churning on that for a while, creating a query execution plan, like a database, that will hopefully be a good starting point. Starts executing that and is handing you back results iteratively, right? But as it's doing that, if it sees any information in the process of gathering the results that looks promising as a new data source, new Sparkle endpoints or linked data that it's found that looks like it might have new information for you, it can augment the query plan it's currently working on with that new data source without throwing away any of the old work. So this allows you to kind of find new data sources that you didn't know ahead of time and hopefully get more results than you otherwise would have found with just the sources you knew about. So that's a Sparkle Federation. Complementary to that, to improve the performance of executing all of these Sparkle queries against all of these Sparkle endpoints everywhere, I developed a caching system that lets Sparkle endpoints participate with HTTP caching, which allows your web browser or other Sparkle clients to use previously generated Sparkle results instead of single Sparkle servers having to execute the same query over and over and over again when you're just going to get the same result. So that's it, federation and caching that helps the performance.
All right.
Hey, Greg, tell the group who your outside reader is.
Tim Berners-Lee on the committee.
So, FYI, that was exactly 2 minutes to give you an idea. Who's on deck now? So Ping is after them.
Hello, everyone. I'm James McGillis, fifth-year resident in the Department of Science Department. And my research interests center around ways in which we can generate explanations for semantic web-driven systems. Now, one of the original goals of the semantic web was to create this web of machine-readable data that agents could in turn act on and produce results for consumption of users. Now, as a means of establishing whether or not users should use or trust given results of these systems, the ability for a system to be able to explain the processing of a flight to generate the results becomes important, as well as establishing those kinds of information used to generate the results. In this work, what I've been doing is looking into ways in which we can fundamentally present different kinds of useful explanations based off of a user's background and in what they would fundamentally be using the explanations for. As an example of this work, one system I've been working with is a system designed to generate visualizations of solar activity for scientists. Now, the people that would be consuming explanations of the system's activity vary in their background as well as what they've used the explanations for. We have people who, for instance, would be responsible for designing the system, people who would be who want to consume this information that's are not actually involved with the maintenance of the system, as well as people who have a general interest in the data products, but not have much background in the science behind them. Now, factoring in both how these explanations will be used as well as background knowledge is something that I've been looking into across several different systems within our lab, and is one of my current focuses for my research.
All right. So, that was exactly 2 minutes. That's awesome. Okay, next is Pink.
None of them ready to be professors. It's 3 minutes to clear your throat.
Hello everyone. My name is Ping Wang. I'm 30-year graduate student. So I've been working on the Semanta, which is semantic water quality model for investigating water pollution in the U.S. It's a web portal, and you can input a zip code and click the go button, and then the portal will find out if there is water pollution in the region specified by the zip code. And you can customize your query, like choose the data sources, and specify your health concern. And to build this portal, we have ontology families. We have upper ontology for generally for environmental monitoring. We also have a domain ontology for the domain of water quality. And we use our linked data approach to integrate the data from USGS and the EPA. And another feature of the portal is about provenance. We capture provenance because things to CSV query follow the capture provenance for us. And we make use of the provenance to do some provenance-aware service, like our facet of the data source is built from the provenance. And this semester we extended the portal to incorporate the wildlife monitoring. We are working on visualize distribution of birds in the U.S. and also investigating how the water pollution will impact the health of the birds. So in the future we have frogs, bats, so becoming cooler. Thank you.
And Ping, tell everyone where you'll be working.
So after this semester, I will go to Seattle and work for Amazon.
And we hope she's going to come back and finish her PhD.
No, it's Jim.
Or at least get us a discounted
It's not
Amazon.
Jim?
Yeah, you forgot.
Oh, yeah. Sorry. I knew you were ready to go.
I can wait. Hi everyone, my name is Jing, 30-year PhD student.
student in computer science. So my research area is on semantic similarity and using semantic similarity to build some applications on semantic web. So recently I'm working with leaning on using semantic similarity to build an instant matching tool. So we think this problem is interesting because a lot of semantic web applications is built on semantic integration. So finding two instance spaces the same is an interesting problem. So we built this instance matching tool using a semantic similarity algorithm. We basically apply three semantic similarity algorithms. First one is using concept similarity or just idea type similarity. Second one is using information content similarity, basically tokenize the description into words and then compute the similarity between the description of two instances. And the third one is feature similarity, basically take each triples of that describes an instance and compare if they any triples any triple that describe the instance in the same manner. For example, they have a car has the same color, so we take that. And then we also try to build this system at a bit scale. So we applied blocking algorithm. So hopefully that can perform a little bit better. And then we also, right now we're working on an experiment, and we download a benchmark from one of the college instance matching organization. And then initial testing result is pretty good. And then we are working on using more test data to see if our algorithm actually works pretty good. That's it.
All right.
Folks, it's a big room. Talk loud.
And actually, can we add where people will be this summer? Also, it doesn't come out of your time. So, are you going to be here this summer?
I'm not sure yet. I need to talk
Oh, okay. And so, Kim's going to be working. James is going to be here.
Yes.
And that's Greg. You're right here. Okay.
I'm Jim McCusker. I'm a third year PhD student in computer science. That was my advisor. I also am a software developer at Yale University in the School of Medicine. And that actually informs, that actually informs what I'm doing here. So I do a lot of work with biomedical semantics there in terms of data interoperability, and I research scary diseases like melanoma. One of the nice things about melanoma is that it's rare. That's about the only thing that's nice about it. But unfortunately, it means that it's really hard to find good data about it. There are very few data sets, and they're even harder to find than people with melanoma sometimes. But the thing is that there's, over the past 12 years, institutes like NIH and the European Bioinformatics Institute have managed to aggregate over 28,000 biomedical experiments. These are very large whole genome, see everything that a cell is doing, experiments about various diseases. And so when I title this talk, I tell that there's science in the dark hills. Each of us could probably take an entire career just reanalyzing the data that's in there. Because in addition to being published, it's also underanalyzed. There's a lot less analysis that's been going on with these experiments than you would think. And so there's a lot of knowledge, a lot of potential publications, stuff that has come out of it. So what I'm looking at is how do we actually take this information and make it represented in a consistent way? How do we take the provenance for that information and set it up so that these experiments are discoverable and potentially find out whether or not we can tie experiments together, and basically taking things for people who have basically flung up some data and have some information about what they think of it and how they think of it, and take that and put it into kind of a more solid semantic structure that we would normally see on the semantic web. And so pretty much everything that I've been doing has been towards that end, things like provenance and data and
information abstraction, things about conceptual modeling and tying that to ontologies, things around data visualization. These have all been things where I've been trying to make it so that people can very easily explore this vast amount of experimental data and tie it together easily.
All right.
Yale this summer.
That was 2:45. No, Bob missed it.
Hi, I'm Bastian Martin. I joined RPI in
You have to learn to yell, Beth.
Hi, I'm Bastian Martin. I joined RPI 2 months ago, so I'll definitely get less than 3 minutes. I will offer my extra minutes to Dominic. You need more. So I'm working on social media data infrastructure. As you all know, social media is taking the main role in our daily lives, in our personal life, how we interact with our colleagues, etc. But not also on the personal life, but also on the nation's life. As you know, the Arabic Spring just started and was reported by social media. I came from Tunisia, where the Arabic Spring started, and social media played a major role in that. You have to know that in 2008, back in 2008, there was just a tentative for uprising, but it didn't succeed. Why? Because at that time, not everyone had the smartphones and not everyone has a Twitter account, etc. In 2008, it succeeded in major role because of Twitter. So that offers huge research opportunities for researchers. One of the major questions now, how these events are triggered through social media. What are the models for diffusion of these tweets or these social interactions? What are the models to model the behavior of the users, etc. Many partners interact in these questions. We need social scientists, we need models from the social behavior, we need different partners and different skills and different expertise. Our goal is to build the data infrastructure where these partners will interact with the data with complete transparency and with the most robust way. Here comes the benefits of the semantics and the RDF. We're building the data infrastructure for these partners so everyone will consume and produce this data in a transparent way without being aware of what others are consuming or what others are doing with the data. So here are our most research question: how to model the data in the most robust way. And I got an open question for semantic web evangelists like Jim. The question is that I keep asking myself all the time: why does semantic web guys wait for killer application like Twitter or whatever to say, okay, now we can do it in a better way with semantics? Why doesn't the semantic web guys come with a killer application saying, okay, this killer application wasn't possible before the semantic web? Thanks.
So you have any candidates?
Yeah, that's the hard part. One of the things I asked Basma if he'd be willing to do, and we just haven't got around to scheduling yet, is actually to do a discussion at some point for anyone interested in what happened in Tunisia. And sort of, most people have heard a lot about the Arab Spring, but not from someone who really was there and involved. So I'm seeing a lot of people around the table going like this. So let's try and add a 2-hour to-do agenda. I was thinking not as a TWED, maybe like in the afternoon around a lunchtime or something, maybe near the end of the term.
Yeah, that's good.
So we could do like a lunch and chat or
Brown
something.
bag lunch. All right.
And people could get lunch. Yeah.
Rude. All right.
About Deborah's question, if I'm staying here, I got an opportunity in France, but I just got an email from the international Jane had to say that maybe there was problems if I can work outside the campus. So I'm not yet sure.
More than welcome to work with us.
Evan is next.
Hello everyone, I'm Amrita and I'm a graduate student in information technology and I'm working is Array for TWC for the semantic e-science framework, and I'm working on the ontology evaluation group with joint Luciano, and I'm currently working on the general ontology evaluation framework. So basically, whenever we develop a semantic-based project, what the first most two important steps which we do is first we decide on the use case, and secondly we decide on the ontology which we can reuse or which we want to develop for implementing the use case. So most of the time for big projects, what we do is we try to reuse an existing ontology, but sometimes it may happen that currently people select an ontology based on the best of their knowledge, but it may happen that the ontology which we have selected it may not be that suitable for a use case, and if it is not particularly suitable for their use case, it may happen that a component of the project can fail in the later run, since both the ontology and use case are incompatible. So the general ontology evaluation framework, basically it provides a framework by which we can evaluate if an ontology is particularly suitable for a use case. So we do a context-based evaluation, use a set of metrics by which the ontology is evaluated, and GOEF basically provides output, like it takes a use case as an input, it will take the ontology, it will do a context-based evaluation, like the ontology is evaluated in context of the use case based on a particular set of metrics, and output is given which will indicate, like suppose there are 10 metrics, so 10 metrics, so this ontology and this use case are ranked so and so, or they pair so and so for a particular set of metrics, and this helps a particular user determine if a particular ontology is suitable to a particular use case. And this can be done before implementation, so this can also help ontologists determine how useful the ontology will be for a particular use case, and it will also help avoid project failure by selecting a good ontology for a particular use case in a particular context. Thank you.
So hi everybody, my name is Evan Patton. I'm a third year PhD student, and my focus is on reasoning and mobile devices. I'm going to be at Qualcomm this summer doing some research there. So the title of my talk is Interruptible Distributed Reasoning on Mobile Devices. And so why would you want to do such a thing? Excuse me. Well, why would you want to deal with interruptions? So on mobile devices, you have a lot of things going on. You have other applications that may need to run. The user may decide that they want to run a different task. You may get a phone call in the middle of dinner or in the middle of a talk. And because of that, you have to deal with writing your state out to memory so that the other application has time to run and has the resources available to do so. And then when your application resumes, you have to load it all back in again. And so I've been trying to look at ways of optimizing how you could actually do this on a mobile device to try to take as little time and resources as possible so that this is a seamless transition as we can make it. There's also issues of connectivity and availability of nodes. So for example, if I go off to the bathroom or something and I walk out of range of everybody else, maybe my phone stops talking to yours. Maybe I get a low battery and so I quit the application because I don't want to waste my time on that particular process. And it might also be the case of having a good enough solution, right? So maybe I don't want to spend 40 minutes trying to reason over an LDL ontology, but if I can spend 30 seconds and get maybe 5 good answers, that is sufficient for my particular application. So the goals are to really, that I've been working on this semester, really to quickly save and restore state. That includes things like storing where in the execution tree I was and the data both in the inference graph and in the raw graph. Looking at estimation of completion time, so we can have metrics and actually try to have a way of saying, well, you know, we expect that it's probably going to take another 10 seconds for this DL operation to complete. Would you like to continue or not? and also looking at asynchronous communication for these distributed networks, so that if my device is trying to solve a problem and it needs information from your device and it can't retrieve it, at least trying to ask your device, could you solve this for me, and then send me something back in situations where bandwidth could be extremely limited for various factors. Thank you.
Hi everybody, I'm Amar Vishwanathan, and this is my first year in TWC, so first year PhD student in bioscience, and so I'm going to have very little to talk here. As of now, I'm working with Professor McGinnis on a diffuse project and developing some sort of visualizations, but I'm more interested in language processing using semantic web technologies. So just to give you a heads up, what we understand is language. Language is basically nothing but a set of words or morphemes on which you impose a structure, and the user uses this to convey his thoughts. And this is one of the classical problems of artificial intelligence experts who've been researching on how machines process language. And this is a very advanced field. It's been there for quite some time, and there are interesting systems developed, and there do exist systems which can process language fairly well. Now, what all these systems do is basically take on given sentence or whatever you say, and they use a syntactic structure and also use some statistical and probabilistic methods to determine how similar what you say is to an existing system. Now, there are certain, I see that there are certain problems in this, because most of what we speak is governed by context. Most of what we speak also, and it requires some context, and you need to, it essentially conveys a set of semantics. And let me give you a classical example of two sentences which are syntactically similar. So one of this is, time flies like an arrow. This is basically, time flies like an arrow, and fruit flies like a banana. So if you give it to a natural language processing system which uses statistical methods today, they rely on syntactic structures, so both of them are going to give the same output, because the system doesn't understand that what flies in one sentence is essentially fruit flies like a banana. Flies are basically an insect, and fruit flies essentially are an insect, and any other system is basically a bird. So essentially what I'm trying to say here is that the semantic will provide you an opportunity to infuse context into any system. So I'm trying to use I'm trying to see whether you can use the power of semantic web, basically the power of using these tools which provide context, and apply them to language processing, and see whether you can get systems which are more which understand the context and which understand semantics much better. And that's about it. Right.
You is after Dominic.
So my name is Dominic Alfonso. I'm a third-year PhD student in computer science. I guess for the summer. I'm going to be here for the summer. Nothing interesting. My work is in trying to apply the power of semantic web into the social sciences. So the social sciences for many years have been developing different models and theories and concepts to help understand human behavior and human interactions. The problem being is that coming up with these theories and coming up with these models, they're very difficult to verify, they're very difficult to duplicate, they're very difficult to use those ideas to help us in building different communication or community software. And the reason for that is that actually gathering real-life human interaction is insanely difficult and really expensive. Having these types of experiments, having enough sample size to verify these things is hard. But lately, with the web, with different virtual communities, with different online communities and different massively multiplayer online games, social scientists have access to a large trove of different people interacting and working together. And we can use this type of data and information to help verify these theories and to help see patterns and concepts and ideas, and to make social science stronger. this idea that Knox Contractor likes to call computational social science. But there's still a big issue with this. We have these large data sets, petabytes in size. How do we manage this information? How do we visualize it? How do we publish it? How do we match this information with other different data sets? How do we know where this data set came from? How do I know what this column in this section of the data actually means? As I've been working with different social scientists and working in different laboratories, I see these concepts and these problems come up again and again. They have all this data, but they don't know what they have access to. They don't know how to use it. They don't know what else people has done to it. They don't know how to clean it. And it's difficult for them. They don't have that computational background. And so my work is trying to show that the semantic web can be a possible solution to this, that by leveraging the semantic web methods and tools and technologies we've used in the Link Open Data world and in our Open Government Data initiatives, we can apply these processes and ideas to the social sciences and be able to really bring out the potential of these large data sets to further understanding of the social sciences.
Right. So you is next. Oh. Okay. Yeah, so you're next.
Hi everyone, my name is Xian Li. I'm a third-year PhD student in computer science department, and I'm studying and I'm interested in the investors' attention on the social web environment. And this is important for two reasons. First, more and more investors begin to gather information online, and so they're exposed to multiple streams of information and quite heterogeneous ideas, opinions. And under such scenario, the attention of the investor will become a very rare resource, and it's a valuable economic resource because when you pay attention to one investment, you ignore and lose the opportunity to other investments. So to study this problem, I've been looking at the group of investors on Twitter, and the measurement I use is the inter-tweet time, which is defined as the time interval between the two consecutive tweets that they made for different investments. And to quantify this matter, I studied the statistical distribution of this measurement. And so first I did the empirical study, which generally has the two hypotheses. One is does investors pay attention randomly, because the randomness or the randomness corresponding to a Poisson process, which is what we use to model human behavior. And so this is the first hypothesis test. And the second is a lot of recent study about the cognitive neuroscience or the financial market have identified the existence evidence of habit tails, which is the scaling pattern or the long memory process of the investor's behavior. So this is the second hypothesis, just to test whether the distribution, the inter-tweet time also exists habit tail. And based on the empirical evidence I find from the actual data, I proposed a model which is made the minimum assumption about the investor's attention process, but to admit the attention is an economic process. And the output of the model is to predict how soon you can see the next time the investor paid this attention after you saw last time he paid attention to this investment. And so the contribution of this model is to rationalize the different distributions I found from the empirical study and to differentiate the rational behaviors, underreaction and overreaction. That's it.
Hi, my name is Ming Fu, second-year PhD student in computer science. Today I want to tell you something about my scientific data photo generator project. And today, more and more of the scientific becoming data oriented, and data portals are becoming more and more important to the advance of scientific research. But on the other hand, scientists are not necessarily good programmers and portal builders and designers, but they know a lot about their data, and they can describe their data precisely. So my scientific data portal generator has the goal of helping the scientists to focus on the job they are good at, which is to describe the data, and left the rest of the work to the generator. That is to apply the best practices in portal building and designing to build their portal. So far, I realized that this project is a very ambitious one, and it can be further divided. So far, I have recognized the following sub-projects, which is use case ontology, which helps to describe the requirements and the goal of the data set, which are held by the scientists. The second one is portal ontology, which describes the widgets, the front-end widgets and the back-end components of the scientific data portal. And the third one is the reusable portal components, which we can see from the modules in the Drupal site. And the last one, but not least, is the data integration module, which merges the data from different sources. So that's it.
Someone plan, yeah.
Oh, yeah. This summer I'm gonna go to G Global Research Center. Thanks.
Congratulations.
Hello, my name is Han Wang, a first-year PhD student in multidisciplinary science program, not computer science, not content science. So for the summer, I might go for an internship in a marine biology laboratory, but it's not finalized yet. So I'm going to talk about a course project of mine, which is called ontology-based text classification. So the idea is that I want to given a piece of text that comes from for example a news story. I want to classify it into one or more categories such as sport or politics. So currently most of the approaches are based on statistics or text mining or natural language processing, and which require a training set to train a classifier, and then the classifier can be used to deal with the data to classify them into categories. So the problem of this is that not always the training set is available to users, and you can imagine that for different data you might need different classifiers. So the approach I'm trying to work out is that I want to make use of an ontology with well-formed taxonomy and lots of instances. For example, Wikipedia. So I want to use Wikipedia. So when I got a piece of text, I want to use Wikipedia to annotate or extract concepts or terms from the text. And more ideally, I can also extract the relationships from the text. And with these extracted concepts and relationships, I can build basically I can build an instance using RDF or something else. And now I have this instance. I want to match this instance to Wikipedia again, and hopefully with using some semantic similarity and to find out categories this text might belong to. So that's it.
Thank you.
Hi everyone, I'm Alkei. Rajesh, fourth-year PhD student in computer science. I'll be here for the summer. So it's been over a decade since the inception of this idea of semantic web. So now sharing data as information is the new normal. So whenever you're publishing data, it's considered just normal to have an ontology that gives the semantics to the data in there, and you link your data with that ontology. And this has given us great many advantages, like greater data interoperability, data fusion. Suddenly you can combine data from different domains, but having overlap and do greater analysis very fast. You can also have data about similar domains, but in different ontologies, and they coming together. And for that, all you need to do is establish relationship between ontologies, between respective ontologies. Now, there is an important piece of knowledge which hasn't gained similar attention, or we don't yet have an ontology language for that, and it's a very important piece of knowledge, and that is continuous processes. I mean, processes that basically describe how a system evolves over time, and this could be described through algebraic equations or differential equations and those sorts of things. So what can happen once we have an ontology language even for processes is that you can now fuse data and processes together, and there's a lot of different types of analysis that you can perform with, given process information and temporal data, or things like time series data analysis, things like trying to understand what processes are happening given the data set that you have. And you can do things like planning, you can do simulation for future predictions, those sorts of things. So there is one approach that you could probably take, that would be to annotate, so have the current ontology languages and create an annotation for the different process models that are out there. Many of these have been implemented in libraries of procedural languages. You have libraries that implement those. But what that can do at best is allow you to, it would act as an index, so that would allow you to pull the relevant data that you want from the web, and to pull out the relevant process information, or the libraries basically. But that would just act as an index. We are planning to take a more radical approach, and that is to actually have a language, have an ontology language, wherein you describe the dynamic behavior, which is described through differential equations. That's the most general form. You can use closed form of equations, and so you associate preconditions, boundary conditions, until when are those things going to be active, and you also specify, and we are also going to specify interactions between processes. So that's the reason why we have been looking, or we have been working towards a web ontology language for continuous processes.
Right. He wants to use it. And I think I'll give him a chance.
No, wait for Jim.
3-minute rules can be waived for faculty. You're out here till midnight if you don't behave.
So my name is Tim Lebo. I'm a third-year PhD student in the cognitive science department. In the summer, I will be living 2 hours away, probably coming in once a week. So my ultimate objective is to build a system that automatically determines what visualization to construct, based off of an understanding of the user, what they're trying to achieve, as well as the characteristics of the data. So over the last 2 years, I've been focusing on characteristics of the data. And in order to build a generic system that is able to reason about both the data and the context of the user, it's really important to find the right infrastructure. So adopting the semantic web infrastructure as a basis for the data representation. So within the context of the linking open government data, I've been designing and implementing a tabular converter to construct RDF, which is both well-structured and highly connected, which is making good RDF out of disconnected data sets. And so the design here both gives you the ability to quickly and easily construct RDF, but also gives you the ability to revisit based off of your particular interests or your motivation to create much better, higher quality representations of that data. The problem with kind of the general RDF converter environment is that lots of systems are doing it. So if lots of systems are doing it, the question becomes which systems are better. And a lot of the focus in the last couple of years has been the characteristics of the systems themselves, but not the characteristics of the data that they're actually producing. And so that leads to the question of what is good data? What is good output from this? And I think that the question to that can't come out as a generic good or badness rating. It really comes down to the context of how that's actually being used. Also, you observe that within the semantic web community, a lot of discussions, a lot of the lore of what is good and what is bad still exists by word of mouth. So I see an incredible irony that we're not using linked data to actually work to generate better linked data. And so that's what motivated the creation of the project that I call Data Facts, which is a linked data quality evaluation framework that basically boils down to allowing you to describe data sets as well as allowing you to host evaluation services, allowing other parties to basically compose evaluating particular data sets that they're interested in against the evaluation services that are available on the web, so that you can have different data facts nodes throughout the web that are focusing on data sets that those particular users are interested in. You're actually creating a linked data about linked data itself that you can then leverage all the benefits of linked data to understand what people think about linked data. And that's it.
Okay, I've asked Christine if she would just say a couple words to introduce herself to you all. So her talk is titled Hello.
Okay. Hi, I'm Christine Goria. Obviously, I've not started my PhD. I'm from Texas, so I ask your forgiveness if I say y'all.
Hey, y'all.
I'm probably the most non-traditional person in this room. I actually am a social science, is my background, social scientist. I came from communications, University of Texas in Austin, my bachelor's and my master's there. So where I sit right now is pretty much at the intersection of information communication and technology. That's where I've studied the last several years. I actually now work for the Texas legislature, and I worked in DC for a really long time. So my interests lie in that area. Where I see this fit in, I'm not 100% sure yet, but just from listening to what you guys have kind of enlightened me with, I see a lot of questions already in my head that I'd like to answer. My thesis was on motivations and uses for Creative Commons, and I think there's a lot to be said in terms of regulation of the internet and what you guys are creating. And so there's essentially a very large gap in what you're creating, what the legislation, what Congress is trying to do, and how people are using it. And so I'm trying to figure out where I can fit somewhere in there and helping fill those gaps. Secondly, currently I live in Brownsville, Texas, and for those who don't know where that is Mexico. I live a baseball throw away from the Mexican border. And coming from there, I realized in the past year that what you guys are creating will not hit that area for another 30 to 40 years. If at, the uptick and the need to teach that area what you guys are creating is also somewhat of an interest for me, because there's obviously another gap, another hill that needs to be tackled for areas outside of metropolitan areas that don't get the internet access or the information that you guys are producing. So that's pretty much where I stand. I kind of am excited to hear more about y'all's projects, and hopefully you guys can help me out. But I'm thrilled to be here. So if you have any questions, I'm pretty easy to talk to.
Okay, so I labeled her talk hello, I'm labeling my talk goodbye, but before you get too excited, it's not me who's leaving. But actually, as you know, Patrick has announced he's moving back to Colorado in the near future.